is x times x times x type stuff here. So you have been playing with exponential functions since about the 4th or 6th grade or something like that. You with me? All right. What grade was it that you first discovered logarithms? 9th grade, 10th grade, 11th grade, some of you people just last year? 10th grade? Okay. All right. My point is this. I first discovered logarithms in the 9th grade. All right? But I was at a special school called Rocky Mount Senior High School. All right, so here's the deal. Public school system. All right. But here's the deal. Yes, I'm actually from North Carolina. Makes me real rare in the math department. All right, so here we go. When it comes to logarithms, we haven't had that much experience with logarithms. We only did this in our high school years, and you haven't left that much long ago for that. So in terms of your background, you should know tons and tons and feel comfortable about exponents. But logarithms, people are still a little shaky on because you haven't had that much experience. So with this stuff, we didn't put on the review sheet here much on exponents because you should know a bunch of stuff here. So let's just solve for these guys. Solve for x on this exponential function. An exponential function is a function of the form f of x equals a to the x. Okay? And so you notice that the x is in the variable of whatever. That's what makes the exponential function. The x is in the variable of the is in the exponent of whatever function. A is called the base. So if I'm going to solve this thing, 2 raised to what equals 4? 2. Well, it wasn't too hard. 3 raised to what is 27? 3 cubed is 27. 4 raised to what is equal to 2? Very good, because 1/2 is also known as a square root. Let me do one more for you that's not on here. How about this one? 2 raised to what is equal to 1/16? Negative what? I hear 3 answers out there. Which one is it? Negative 4. Let's explain why. 2 raised to the negative 4. Where does a negative exponent put you? On the bottom. 2 raised to the 4th. What is 2 to the 4th? 2 times 2 times 2 times 2. What is that? 16. So 2 to the negative 4 is actually 1/16. The negative exponent put him on the bottom. So x would be negative 4 for my answer. Just reminding you guys of some of your exponential properties. Radicals are fractional exponents. Negative exponents makes fractions, put stuff in the denominator. Okay? But now, those are, like I said, classic exponential functions. Again, this is a big review. Again, just reminding you of what you guys did way back when. Part B, logarithmic functions here. This is the thing that most folks don't remember that much of because it was a chapter in some book sometime in the 9th, 10th, 11th, or 12th grade, depending on your background, your high school and stuff. But you didn't do that much with it. You did a little bit of it, and then you moved on to something else. So I've got to remind you about logarithms. The first one is the definition of log. A logarithm is a function of the form f of x equals log base a of x, i.e. the variable x is in the expression, and you're taking the log of it, log, base a of x. All right? Y equals the log base b of x is how you read it. Y equals log base b of x. B is called the base number, and x is the variable. The first thing that you need to learn about logarithms is what I call the definition. Definition of logs is very simple. If I have here log base b of x equals y, the beauty of logs is this. You have the ability to rewrite them if you don't like them. So if you have log base b of x equals y, that's the same thing as b raised to the y is equal to x. So this equation, log equation, and this exponential equation are the exact same equation. Now, when I'm teaching college algebra or pre-calculus or something like that, this is how I typically introduce this to my students. Y equals the log base b of x. When you have a log, you have the ability to rewrite it. It's what I call the smiley face definition. You start with the base, b. You raise them to the other side, raise them to the y. It equals what you're taking a log of, equals x. And it makes you look like a little smiley face there, and people remember this kind of stuff. And therefore, remember, if you don't like logs, you have the ability to rewrite them. The base raised to the other side equals what you're taking the log of. Okay? B to the y equals x. Now, that being said, again, some quick examples here. Write each equation in its equivalent form. This one is logs. These three are logs right here. I want you to rewrite them in their equivalent exponential form. X is equal to the log base 2 of 16. Well, this is code. What are they really trying to tell me here? Start with the base. 2 raised to the x is equal to 16. They didn't ask you to solve it. They just asked you to rewrite it. This x equals log base 2 of 16 is the same thing as 2 raised to the x equals 16. Does that make sense? All right. Look at number 2. Y equals the log base 6 of 216. Rewrite it. Start with the base. 6. Raise it to the other side. Y. It equals 216. 6 to the y equals 216. But notice where they're putting the variable at. X equals. But the x, well, remember with logs, what logs are equal to are always the exponents. The x is in the exponent. The y is in the exponent. What about this guy here? 3 equals the log base b of 27. Well, rewrite it. What's your base? B raised to the third power equals 27. If you don't like logs, you have the ability to rewrite it. But sometimes you want to have an exponential equation and you want to write it in log form. Write this guy in log form. The reason why I want to write this one in log form is because we're trying to solve for the exponent y. In log form, you got log. The base is going to be the same up here. That would be base a of, remember, the logs are always equal to the exponent y, and the number you're taking is 300. Y is equal to log base 8 of 300. Double check yourself. Do the smiley face thing. 8 raised to the y equals 300, which is exactly what we got here. So this is my answer for rewriting it backwards. Does that make sense? And notice that it solves for the exponents. That's the reason why we study logarithms. It solves for exponents. Remember that. That's something worthy of your notes. The reason for us studying logarithms is that logarithms solve for exponents. That's why they were developed in the first place. All right, some common properties of logs. Log base b of b is equal to 1. Reason why? Smile at it. B raised to the what power equals himself. Got to be 1. Log base b of 1 equals 0. Reasoning? Smile at it. B raised to what power equals 1. What do you raise anything to get the 1 power? Get 1. 0 power. B raised to 0 power equals 1. This one right here, log base b of 0 does not exist. The reason for this is this. When it comes to logs, log base b of x, the domain of logarithms is x have to be strictly greater than 0. In other words, for logarithmic graphs, for logs, you can only take the log of positive numbers. If you take the log of a negative number, you get an error message. Let me prove it to you. Proof by calculator here. Log, you got some log buttons over here. The log, turning on helps. The log, there you go, you can see it now. The log of negative 100. What do I get? That is the error message you'll get. Non-real answer. Okay? But if you drop the negative, you can definitely take the log of a positive number, 100. That works fine. That happens to be 2. Okay? But you can't take the log of a negative number. It's an error message. You can't take the log of 0. Error message. You can only take the log of positive numbers. So x has to be greater than 0. The other reason why we study this, again, as a reminder, refresher here from your college algebra, high school algebra 2 days, logarithms and exponentials are inverses of one another. And remember, when you take an inverse and you take a composition of a function with the inverse, they cancel each other out and you're always left with x. So the log base b of b raised to the x is x. That's because they're inverses of one another and they cancel. B raised to the log base b of x. B and the exponential, but you got a log in the exponent with the same base b, they're inverses, they cancel. you're left with x. One other one that you must remind yourself of is on your calculator, you will notice that there are only 2 log buttons on your calculator. Now, there are other calculators out there like Casio, and there's a few other ones that actually have special log buttons that you can figure out the base. But standard Texas Instruments style calculators, they only put 2 log buttons on the calculator. What are those 2 log buttons? LOG and LN. LOG is called the common log. What exactly is the common log? LOG is log base 10. This guy right here is called the common logarithm. Common log. And the reason why is it's based on our numbering system. Our numbering system is base 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The next number is 11, 10 and 1, 12, 10 and 2. We have a base 10 numbering system. Since our numbering system is base 10, therefore, any kind of classic math we do, well, it's base 10, so we're going to use base 10 on logs. The only problem with that is, you got to remember, we're mathematicians. We're inherently lazy. So after a while, we got tired of writing the little 10 down here. So we just stopped writing the 10. So if you don't see a base on log, it is understood to be what base? Base 10, called the common log. The other one, I might as well talk about it while it's down here, is that LN button. Now, there's something called the natural number, E, 2.718281828, ... keeps on going forever, never repeating, never ending, irrational number E, called the natural number. All right? And when I take E, that 2.71828 number here, and make it the base on my log, we define that to be the natural log. This is the natural number that shows up in nature naturally. So we're going to be doing lots of natural log problems in here because they're science and engineering style. So our classic log for that is going to be natural log. It is understood, even though you don't see a base down here, that the base is E. And we just write a LN down there. Now, I'm going to pick on some high school students that I had one time. That I was working with them on some logarithmic stuff, and they were working the problem, and they kept saying we're supposed to do this. We're supposed to take line X this, and line X that. And I was just confused because I've never heard of line X. What exactly is line X? Well, that's just some bad math teacher out there explaining they didn't call it natural log in that class. They call it line, LN. I have no idea. That's just a crime. It is LN. Natural log. Log del natural something. Natural log is what LN. It's not line. Don't line at me. I will slap you. All right, so this is called natural log. All right, so if you came from that high school, please don't call it a line. I'm going to find that teacher and beat her up. Okay, so here we go. Let's take a look at these problems and see if we got 10 seconds, see if we can't do this problem. On your mark, set, go. Log base 2 of 2. What's my answer? When the base and what you're taking the log of are the same, property says you always get 1. Number 2, log base 6 of 1 is equal to what? 0. It doesn't matter what the base is. When you take the log of 1, you always get what? 0. What about this one? Log base 4 of 4 raised to the x. Very good. X. That is this property over here. Log base z of z raised to the x plus y. What's that guy going to be? Very good. Logs with the same base as the exponentials or inverses, they cancel. You just left with the exponent. What about this one? Log base, 8 raised to the log base 8 of 12y. What are you going to get? 12y. Because they cancel each other out. And this one, what is the log of 10? Very good. 1. Why? Because even though we didn't write it down here, what is understood to be the base of this log? 10. And when you take the log, the base, and what you're taking a log of with the same thing, they end up canceling, and this becomes property number 1 again. Okay? Natural log. What they want you to do on this one is you never write log base e. That has a particular functional name. We're going to use that functional name. What is log base e of zx equal to? That is the natural log of zx, and this is the way you're going to view it. Natural log of x. In this case, the 3z. And this one, what is the natural log of e? Very good, it's 1. Natural log and e's end up canceling. The fact is, this is a log base e, and when the base and the x and what you're taking a log of are the same, they cancel out. You get 1. But, more importantly, we also have, or equally importantly, we also have the classic log properties. Now, you got to remember, logarithms and exponentials are inverses of one another. They're inverses of one another. So, that being the case, let me remind you of some exponential properties. Logs and exponents, exponentials are inverses. So let's look at exponents for a second. A raised to the x times a raised to the y. When you multiply with like bases, what do you get to do with the exponents? You add them. A raised to the x plus y. Division, a to the x divided by a to the y. Well, with multiplication turns into addition, what do you think division is going to turn into? A to the x minus y. And the third rule was a to the m raised to the n. Power raised to another power with exponents. What do you do with exponents? That would be a to the m times n. There were some other properties as well. For example, anything to the 0 power is 1. Anything to the first power is himself. Negative exponents. Where do negative exponents get to go? On the bottom becomes 1 over a to the n. And the fractional exponents. A to the 1 over m power is the same thing as what? The nth root of a. So 1/2 power is a square root. 1/3 power is a cube root. And if I continue on, a to the m over n would be the nth root of a to the m. These were just some classic exponential properties that you no doubt know. But remember, exponentials and logs are inverses, which means they do the complete opposite. However, because they are connected, they do have similar patterns. Look at your log properties. The log base b of m times n. That's equal to the log base b of m plus the log base b of n. Multiplication with logs turns into addition of each one. Multiplication turns into addition. Division, log base b of m divided by n is equal to the log base b of m minus the log base b of n. Division turns into subtraction. And log base b of m raised to the n, well, that's like a power to a power you get to multiply, but if I want to multiply this, the n gets to pop out front. That's equal to n log base b of m. These are your three big log properties right here, okay, called expansion properties for logarithms. So, take a look at these directions down here. Simplify the following using these log properties. Well, some of them we've done before, but let's take a look here. What is the log base x of x times z? Multiplication turns into what again? This will be the log of x, log base x of x, plus the log base x of z, because multiplication turns into addition. But you're not done. Clean it up as much as possible. What is the log base x of x? Well, when they're the same base as what you're taking log of, they cancel, you get 1. So the answer is 1 plus the log base x of z. Does that make sense? All right. Simplify. Log base 3 of 27. Well, what they were really after was this. Log base 3 of, what exactly is 27? Break it down. How about 3 times 3 times 3, which is also 3 cubed, because I am trying to write it with the same base as what the log is. Because when that happens, they clean up and cancel. So what's the answer? The log and the exponential cancel. You're left with the exponent. The answer is 3. Same idea down here with this one, just to kind of remind you of the inverse of what we did here. The 8 raised to the log base 8 of 12y is what? Just 12y. That is my answer there. And then last but not least, what is the log of 10 raised to the x plus y? What would that be? No, not natural log of x. No. How about x plus y? This is log understood to be base 10, even though we don't write it. And when the base and the exponential are the same, they cancel. You're left with the exponent, x plus y. All right, this one. Look at the directions. Expand the following logarithms. That means you want to bust these guys up in terms of multiple logs. First things first, I got log base b of x times y quantity cubed. Since you're taking log of something to a power, where do powers get to go? To the front. This becomes 3 log base b of x times y. But This is multiplication. Log base b of x times y. What does multiplication turn into? That would be 3 times the log base b of x plus the log base b of y. And if you want to clean this guy up, I would distribute the 3. That becomes 3 log base b of x plus 3 log base b of y. And there's my solution for that guy. Clean him up. Does that make sense? Compare that one to this one, though. With this one, order of operation is different. This one, it's x times y cubed. So the y only has the cube to it. Does that make sense? Subtle difference between this problem and this problem. Notice where the parentheses are located at. But this is still multiplication, and multiplication turns into addition. That'll be log base b of x plus, adding, log base b of y cubed. But you're not done yet, because this little log has a y that's being cubed here, so therefore, where does this cube going to go? In front of the log of which it's attached to. So the answer would be the log base b of x plus 3 log base b of y. And there's my answer for that guy. This one here, number 7. I ask you this. What is log base b of x cubed times y divided by z squared? Well, we're going to bust this guy up. Multiplication turns into addition. Division turns into subtraction. This will be the log base b of x cubed plus the log base b of y minus the log base b of z squared. However, you're not done. Where do exponents get to go when you're cleaning up logs? To the front. This is equal to 3 log base b of x plus the log base b of y minus 2 log base b of z. Does that make sense? Yeah.
So you wouldn't put a parentheses around the log of x and the log of y? Like,
I mean, if you wanted to, you could do that.
No, like,
do that.
The addition part, you wouldn't put a parentheses around all the addition part?
Oh, no need to. Because you can drop the parentheses because it's being added and subtracted. You got to fewer the parentheses, the better when it comes, especially when you're typing this into a computers and stuff like that. This is fine. You bust them up, turns into addition. What about this guy here? This is equal to the natural log. I don't do square roots. So this is ex to the 1/2 power. Where do powers get to go? Out front. So this is 1/2 the natural log of e times x. Now this, I do want to bracket here because I'm going to bust these up, but the 1/2 is in front, and it's going to be in front of both of them. Unlike this one over here that it wouldn't have mattered. All right? Multiplication turns into what? That'll be the natural log of e plus the natural log of x. But clean it up. This is 1/2. What is the natural log of e equal to? That is 1, because this is understood to be base e, and of e cancels, get 1 plus the natural log of x. And then I would distribute, just to give me answers, 1/2 plus 1/2 natural log of x. That would be my solution for this one, cleaned up. Okay? Yeah?
I know sometimes you're putting like the natural log in parentheses, and sometimes you don't. Does it matter whether you do or don't? Or?
In terms of these x's, no, it really doesn't. I was just trying to be fancy because I did it over here. Now I'm doing it over here, but there, I've done it everywhere now. There you go. All right, next guy right here. First things first. I don't do square roots. What's a square root? 1/2 power. All right, multiplication turns into addition. Division turns into subtraction. So this is the natural log of x to the 4th plus, because it's being multiplied, the natural log of x squared plus 3 to the 1/2 minus, because we're dividing, the natural log of x plus 3 to the 5th. But we're not done yet, because where do exponents get to go? Out front. So this is equal to 4 natural log of x plus 1/2 natural log of x squared plus 3 minus 5 natural log of x plus 3. And there's my answer. One last thing to remember about this particular stuff is this. You never get to distribute a log. Because I got the natural log of x squared plus 3, that's not the same thing as natural log of x squared plus the natural log of 3. That's a violation of math. The reason why is this. Remember my log properties. Multiplication turns into addition. division turns into subtraction. So if I try to distribute these logs, it's going to mess up these properties. So never distribute logs across a plus or a minus. If you have multiplication, you can turn that into addition of the log of both terms. Division turns into subtraction of the log of both terms, but you do not get to distribute logs. Let me do one more. Okay, let's see here.
Like terms, like you have 4 natural log x plus
5 natural log of x. Now that you can combine. That will be 9 natural log of x. But that's just adding like terms. But we're talking about what the natural log of x plus y, that does not equal the natural log of x plus the natural log of y. Because the reason why is this. Now work your log properties. Addition turns back into what? Multiplication. That'll be the natural log of x times y, and that's not the same thing as x plus y. This does not work. You never do this. All right? All right. Let's see how good you guys are. I'm going to give you guys 30 seconds to do this problem. That should be all you need. On your mark, get set, and go. This problem is log of 100 times x plus 3 divided by z times x minus 4 cubed. I want you to rewrite this in terms of multiple logs of your single variables. Bust this guy up. And when you get an answer, raise your hand, and I'll write it down, and we'll figure out, we'll make an election out of this and see if we can get the right candidate. All right. Who's got the right answer? Raise your hand. That's right. I expect you guys to be done in 30 seconds or less. All right. Give me an answer. Go for it. What you got? Log 100 plus log x plus log of x plus 3 minus log z minus 3 log x minus 4. You do that. All right. Any other candidates? Yes, sir.
I got log of x plus log of 100 plus log of x plus 3 minus log of z
Hold on. X plus 3 minus log of z. I'm with you. Go for it.
minus 3 log of x minus 4.
Let me write all that. It's the same thing. Who cares what order they're in? Okay, fine. Any other candidates? Anybody else? I mean, these are the only 2 answers everybody got, and they're the same answer. Everybody got this? I don't believe you people. No other answers. What about plus here? What about this one? The log of x plus the log of 100 plus the log of x plus 3 minus the log of z plus 3 log of x minus 4. What about that guy? Did you get that one? All right. So, yes, sir. Got another one? 2 plus log of x All right. So let's vote on these guys. We got 4 candidates now. It's kind of like the Republican thing last night. All right. So let's vote. Figure out who candidate we want to vote for here. How many people vote for the first one? You should always vote for yourself. Give yourself honor. There you go. All right. Who votes for the second one, being it's the same as the first one? Vote for the same guy then. All right. So we'll group these 2 guys together. How many people think it's 1 and 2? 1. All right. All right. Well, it doesn't. Okay. What about number 2? Well, I guess this will be candidate number 2 now. How many people vote for this one? 1, 2, 3, 4, 5. 5. I hear only 5 people. 6. 6 people vote for this guy. How many people vote for this one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right. 15 people voted. Just like our last election, we have a total of 21 people voting. There are 49 students in this class. Yep. Okay, fine. Luckily, the 15 people did vote for the right candidate. This is the answer. Let me explain why. Oh, no, well, the deal is this. You guys did it right. Multiplication turns into addition. A lot of people put, and I'm surprised, I'm proud of you guys for not putting the log of 100x. This is a number. I don't care if it's a number or a variable. If it's being multiplied, you can bust him up with a log. This will be equal to the log of 100 plus the log of x plus the log of x plus 3. This is in the bottom. Bottom denominator means divide. Divide means subtract. Minus the log of z. Even though it's times right here, you got to remember, where is it located at? You're looking locally. You need to think globally. This is a fraction. X minus 4 cubed is located where? On the bottom. Bottom means divide. Denominator means divide. That'll be minus the log of x minus 4 cubed. And where does exponents get to go? Out front. But here's the thing. What exactly is 100? What exactly is 100? It is what? 10 squared. And what is the log of this guy right here? What's the base right here? Understood to be 10. So what is the log, base 10 of 10 squared, also known as 2. So you get the answer 2 plus the log of x plus the log of x plus 3 minus the log of z minus 3 log of x minus 4. There's my final answer. And yes, sir, you had a question.
For the z log of z, the log of
Yeah.
when I did it, I mean, it's basically the same thing, but I just cut the negative.
You can keep the negative out and put a parenthesis here and put a plus and then distribute negative. That's fine. But we're doing math, and we're doing math quickly because this should be a review. So in terms of doing that, which gives you 2 steps to do it before you get the answer because you got to take the extra step of distributing, you can, well, it's in the denominator. Denominator means divide. Divide turns into subtraction with logs. So it makes it a minus. Oh, that's perfectly acceptable. But again, I'm trying to go for the answer 1 correctly and then 2 quickly. All right. All right. But I think of logarithms like this. Logarithms are pretty much the Humpty Dumpty of the problems. All right, Humpty Dumpty. What's the deal here? You got Humpty Dumpty sitting on the wall. What happens to him? He fell over, and what happened to him? Busted a bunch of pieces. Then what's your job now? You got to put Humpty Dumpty back together again. Well, here's Humpty Dumpty down here in a bunch of pieces. Your job now is to put Humpty Dumpty back together again in terms of one big log. Rewrite the following as a single logarithm. Now, you've got to work the property backwards. Now, let me show you something to remind you. In terms of these log properties, we're going backwards. So addition will turn back into multiplication, subtraction turns back into division, and power numbers in front go back as exponents. But before you can combine logs, what is understood to be the coefficient in front of all these logs here? 1. So if you ever have a number in front of the log, you've got to first put him back where he came from before you can combine logs. You've got to have coefficients of 1s in front of your logs before you can combine them. So here we go. I have 3 and 4 in front of my log. So where do they come from? Where do they go back to? Log base b of z cubed plus the log base b of x to the 4th. This turns into one big log base b of, and what does addition turn back into? Multiplication of z cubed times x to the 4th. And there's my answer. Rewriting the logarithm as one big log. Does that make sense? All right, take a look at this next guy. You see this 1/2 out front? I don't like numbers out front when I'm trying to combine logs. Where does he come from? Where does he go back to? Well, he becomes an exponent. That'll be x plus 2 to the 1/2 minus the log of x. One big logarithm, but this time, and by the way, what's the understood base on this particular log here? Even though we didn't write anything. Understood to be 10, common log. This guy is understood to be positive. Positive things go on top. This is x plus 2 to the 1/2. And subtraction turns into division divided by this term x. And this is your answer. Now, if you put it as this, log of the square root of x plus 2 over x, of course I would count that 100% correct. But this is good enough. Does that make sense? You can write it. If you want 1/2 power, you can write square root. That's up to you. What about this guy? Here's the one that messes a lot of people up. It doesn't matter about order. The first thing you want to do, if you got a number in front of a logarithm, you got to put it back in terms of the exponent. This becomes the log base 5 of z cubed, right? Minus the log base 5 of z plus 2 raised to the 1/2 plus the log base 5 of y. Now you're going to turn it into one big log base 5. And here's the deal. Positive things, being positive is plus, what did I do wrong? Oh, square. I'll keep losing that square. Square, thank you. But the 2 goes back in the exponent. Now, the positive things go on top as multiplication, minus goes on the bottom. So this is understood to be positive, so the z cubed goes on top. This is a minus. So the z plus 2 to the 1/2, or square root of z plus 2, goes on the bottom. But this guy's positive again. Where do positive guys go back to? Back to the top, back to the numerator. Y squared, and there's my answer. The one thing you must notice is this. Look at each one of these logarithms. These logarithms are very simply all the same log. They're all log base 5. You cannot combine logs of non-like logs. Log base 2 plus a log base 3 thing you don't get to do. They all have to be the same logarithm. Does that make sense? This one here, if I was going to clean this guy up, the first thing I would do is distribute the 4. Clean up your algebra first. This is going to give you 4 times the log base 2 of x squared plus 4 times 1/2 is what? Plus 2 log base 2 of x plus 4 times 4 is 16 log base 2 of z plus 1. I distributed my 4 throughout as my coefficients. Now there's going to be a little cleaning up on this one, but that's okay. We'll clean them up in a second. Where do coefficients go back to? Exponents. So this becomes log base 2 of x squared raised to the 4th plus the log base 2 of x squared plus the log base 2 of z plus 1 to the 16th. I put all my coefficients back as powers. Clean it up. Power to a power. What are you going to do? X to the 8th. You multiply. So this is the log base 2 of x to the 8th plus the log base 2 of x squared plus the log base 2 of z plus 1 to the 16th. It's all pluses. Now turn to one big log. This would be the log base 2 of x to the 8th times, addition turns back into multiplication, x squared times, parentheses, z plus 1 to the 16th. But you're not done yet. Because even inside parentheses, remember, you got to clean this stuff up. What is x squared times x to the 8th? What is x to the 8th times x squared? When you multiply, what do we do with exponents? You add. This will be log base 2 of what? X to the 10th times z plus 1 to the 16th. There is my final answer. Does that make sense? Have you guys seen this stuff before? Okay, good. I'm just trying to remind you of things you've done, no doubt, long ago. One last thing over here. If you notice your calculators, we mentioned this before, there are only 2 buttons on your calculator for logs. For most calculators. There's some fancy Casios and Hewlett-Packards and stuff that have some special buttons on it. For the most part, most standard calculators have 2 log buttons. LOG, common log, LN, natural log. So what do I want to do if I want to compute a logarithm that's not of either common log or natural logs? Well, there's something called the change of base formula. And this is here's the real change of base formula. It's used for calculators mainly. Change of base formula. And it says this. If I have the log base b of m, that's equal to the log base a of m over the log base a of b. You choose b. You choose a. A is the base. You get to choose this new base a. But if I'm doing something on a calculator, what bases do I want to choose for logs? Either the common log, because I got a button for it, or the natural log, because I got a button for it too. And what they tell you in this particular form, if I got log base b of m, I can either change it to base 10 to use the calculator, log of m over log of b, Or I could use natural logs. Log of m, natural log of m divided by the natural log of b. So let's do this first problem on the calculator here. What is log base 8 of 17? This is equal to, I'm going to choose common log. That'll be log of the original function, 17, divided by the log of 8. This is the change of base formula. Putting it on my calculator, this is what it would look like. Log of 17. But this time you divide by another log, log of 8. And I get the answer 1.362487614. But I wanted to show you this. It wouldn't have mattered if I chose the common log button or the natural log button. Natural log of 17 divided by the natural log of 8, natural log of 17 divided by natural log of 8. You'll notice I get the same digits. I get the same number completely. Let's do one more. What is log base 5 of 15? That would be the log of 15 over the log of 5, or you can choose the natural log of 15 over the natural log of 5. It's your choice. And if you got a TI-89, you'll notice that you got to go hunt for the common log button. All you've got on that calculator is the natural log button being shown to you guys. So let's just do that one. That'll be natural log of 15 divided by the natural log of 5. And I get the answer 1.682606194. Does that make sense?